In advanced engineering, like designing the containment fields for a stellarator fusion reactor, you rarely deal with simple shapes. You are confronted with highly complex, multi-directional electrical coils, and you must calculate their exact magnetic output. The problem is that standard textbook models are usually built for flat, two-dimensional planes. These equations struggle when applied to complex, real-world 3D geometries. To solve this, we need a specific metric capable of tracking the magnetic footprint of these structures. We need the magnetic moment. Look at this standard diagram of a 2D wire loop. The boxed formula at the bottom shows the foundational definition of a magnetic moment, denoted by the letter m. Two parts of this equation are simple scalars. N represents the number of turns in the wire coil, and I is the electrical current flowing through it. But look closely at the final variable, area. It is marked with an arrow over the A. In this context, area is not a standard measurement of flat surface space. It is a strictly defined vector. To analyze 3D electromagnetic problems, we must define area as a directional arrow pointing through three-dimensional space. If the area of a shape is actually a directional arrow, the immediate question is, how do we know which way that arrow points? Direction is dictated by the current's physical flow, mapped using the right-hand rule. Curl your right hand's fingers with the current. Your extended thumb is the perpendicular area vector. If the current reverses, your hand follows, and the area vector points straight downward. When a loop is resting flat on a standard Cartesian plane, finding this vector is simple. The math aligns perfectly with the physical world, pointing straight up or down a single axis. But when we lift that loop and tilt it off the flat plane, suspending it at an angle in open space, visualization becomes more difficult. Human spatial intuition is excellent at judging flat surfaces, but it is much harder to precisely calculate vectors when objects tilt across multiple axes simultaneously. To find the exact orientation of a tilted plane, we need a more formal mathematical method that determines direction without relying on visual estimation. This graph illustrates the problem. We have a square loop labeled ABCD suspended within an XYZ coordinate system. The parameters here are straightforward. The loop has a side length of L and carries a steady current of I. The loop is anchored flush against the vertical y-axis, but it is angled exactly 30 degrees outward into the XZ plane. Using standard trigonometry to estimate the precise perpendicular angle of this tilted face is tedious, and it is easy to make a sign error. Instead, we can translate the physical edges of the wire loop into individual mathematical vectors based entirely on their Cartesian coordinates. Let's isolate just one edge, vector AB. We map its trajectory by breaking it down into its x and z components, yielding L cosine 30 I hat plus L sine 30 k hat. By translating these wire segments into Cartesian vectors, we convert the spatial geometry into algebra. To define the area of this entire square, we need a second adjacent vector that bounds the shape. We take the adjacent side, vector BC. Because it points straight down the vertical axis, it is simply negative L j hat. This setup allows us to use the cross product. The cross product of two adjacent vectors that bound a parallelogram generates a new third vector that is perfectly perpendicular to their shared plane. As shown here, we find our specific area vector by crossing vector AB with vector BC. We distribute the terms, multiplying the I hat and k hat components of vector AB by the negative j hat component of vector BC. The mechanics of the cross product determine the spatial direction. For instance, multiplying I hat by negative j hat results in negative k hat. The math handles the orientation for us. This gives us a finalized Cartesian output for our area vector, positioned correctly in 3D space. To find the total magnetic moment, we simply multiply this area vector by the scalar current I. That leaves us with the final formula for the tilted loop's magnetic moment. The cross product defines the area vector perpendicular to the tilted plane, providing a consistent result without requiring us to visualize the angle ourselves. But we can go further. What happens when a current path refuses to sit flat on any single plane? This diagram presents a more complex case, a continuous bent wire path tracing the edges of a three-dimensional cube. Our previous method hits a limit here. The wire encloses an empty 3D volume, not a single two-dimensional flat plane. Because there is no single plane, there are no two vectors we can cross to find the total area. We have to find a way to calculate the magnetic moment for a shape where a unified, flat geometric area does not exist. To solve this, we can mathematically break the complex shape into simpler, solvable parts. We do this using vector superposition, where we solve a complex system by summing together several simpler ones. We can add virtual currents along the main Cartesian axes to close off these open geometries. This is mathematically valid because virtual currents added along the same lines point in opposite directions. They cancel each other out, meaning the net physical current remains the same. By adding these lines, we are effectively slicing the tangled 3D wire into 3 distinct, flat, independent square loops. Because each of these 3 new loops is flat and aligned to the primary axes, their individual area vectors are easy to define along I, J, and K. As the calculation shows, the total magnetic moment is simply the sum of 3 isolated vectors. By treating area as a 3D vector, using the cross product, and applying superposition, we can resolve even the most complex, non-planar geometries.